Right, guys, gather yourselves. Here we go. So, have you calculated in the past inverse functions? I hope you have. This is a sort of review. So, for instance, suppose I asked you to find the inverse of 3x plus 6. What do? What is the idea of finding an inverse? It's very similar to pressing undo. Yes? So, what is the undo for this operation? In this operation, the input is multiplied by 3 and 6 is added to it. So then I can see that to get back this input x, I have to subtract 6 and divide by 3. So f of x minus 6 over 3 will give me the initial input that I started with. It will give me back. Yes. What do they say? And the soul and my soul from out that shadow shall be lifted nevermore. So here is the situation. So we have a soda machine A and we have a soda machine B. Notice that mathematically what we think of is, yeah, of course I offer partial credit for the exam. By the way, guys, one more question since you're on the exam topic. How far in the exam are you? Do you need more time with it? Do I need to forget when the exam is due or not? Well, I still am grading something else. I'm still working with probability there. So you can, if you want, submit it by next Thursday. Not this one if you want, but next Thursday. And after class, you can ask me anything regarding the questions. If you find something unclear or you want to understand what is meant there, none of those questions, as I mentioned in my email, are requiring hard calculations. If you're spending a lot of time doing calculations, you're doing something wrong or something not optimal. Good? So we'll discuss those questions if you have them after class. And so back to this topic, guys. So soda machine, right? So notice that if number 1 is pressed, you get Coca-Cola. If number 2 is pressed, 1 gets Pepsi, 3 gives water, 4 gives Sprite. So we have this distribution. So as a mathematical object, we think of the soda machine as transforming the number 1 into a soda can, into Coca-Cola, number 2 into Pepsi, number 3 into water bottle, and number 4 into Sprite. You see? So mathematically, this is the transformation. This is the domain A, and this is the range B. You can see 1 is transformed to Coca-Cola, 2 is transformed to Pepsi, etc. Now, function A is invertible because you can see that I can create a reverse operation. I can create an undo operation. So I can I can put Coca-Cola and it will transform it back to the number 1. I can put Pepsi and it will transfer it back to the number 2. In other words, each item has a unique origin and I can trace it back to its unique origin. I can undo what happened to it. You understand? So notice that if I press the two functions consecutively, if I apply f and then f inverse, I am back at the same location. Similarly, if I begin with Coca-Cola and I first go in this direction and then, so in other words, apply f inverse and then apply f, I get what I started with. So that's an example of operations that can be cancelled, can be undone, can be inverted. On the other hand, here is another example, a different soda machine. And we have here that numbers 1 and the number 2 are mapped to Coca-Cola. 3 is to Pepsi, 4 is to Sprite. What happens in this situation? You can see that in this situation, 2 inputs from A are collapsed to 1 output. So when I start with C, I cannot figure out if I should go to 1 or if I should go to 2. So this operation does not have an undo. It's not an invertible operation. Make sense? So inverse operations are operations that cancel the function f. So what's the definition of invertible functions? This is the definition. A function from a to b is invertible if there exists a function f inverse such that the composition of f inverse and f of x will give you x, and the composition of f and f inverse will give you x. Do you understand what this x means? This just means that if you apply the operations in any order consecutively, they will cancel each other out. Yes? So in any order. So this is here f blue then red is f then f inverse. So blue then red is this operation. You see, because you go like this, x then f inverse. So this operation is illustrated if I first go by blue and then by red. And the other operation is illustrated if I first begin with red and then with blue. So this is red first and then blue. Now, for a function to be invertible, as you can see, the function has to be one-to-one, because here's a situation where the function is not one-to-one. That means that two inputs are collapsed to the same output. There is no way to determine what was the origin of the output. Now, I want to remind you guys that f inverse of x is not 1 over f of x. Okay, this notation does not mean take 1 and divide by the number, right? Now, why is the notation -1 used to begin with? So first of all, would anybody like to try to tell me what is the meaning, let's say, of 3 to the -1? Not what it's equal to, but means what? Okay, just grammatically, what is 3 to the power -1? What is that supposed to tell? What operation is it claiming? Well, you see the rule. Yes, the answer is 1/3. It's true, but why is the answer 1/3? Okay, that's the question. So here is how I read this. Anybody wants to say something before I do? So I look at it and I read. Those are yeah, but you're just reading what you see there. Right? You're not telling me what's the word. So in other words, if I were to write stupendous, you are not going to say, I see an S, I see a T, I see a U, I see a P, and onwards. Yes? That's very different from understanding what the word is communicating. So read this means understand the meaning. What's the meaning of it? It means undo 1 multiplication by 3. That's what it means. So for instance, if I have 3 squared and I multiply it by 3 to the -1, by the result, I'm undoing one of the multiplication. It should be 3 to the 1. If I have 3 to the -1 times 3 to the 4, I'm undoing one multiplication by 3. That should be 3 cubed, right? But how do you undo a multiplication by 3? That means what? That means 1 over 3. Just multiply by 1 over 3. You understand? To undo a multiplication by 3 is to divide by 3. That's why 3 to the -1, that's another way to see why 3 to the -1 has to be 1 over 3 to the n. Yes? So we have those properties when you multiply numbers. So for instance, we know that a to the n times a to the n. In other words, if I multiply those numbers, I should get a to the n plus m. You agree? Now, a similar thing happens with functions. For instance, guys, suppose I have a function f of x, right? Let's make it very particular just so that it makes sense. So it's x plus 2. Yes? It's x plus 2. He's trying to open the door. It's good that it's rounded because he can open doors. If it were not rounded, he would have entered. I already have let him in. Yes. To this house. So f of x is x plus 2. This is my function, yes? So what does it mean? What is this supposed to mean, guys? Anybody will tell me? What is f2x? Please write in your comments. Okay, Francis says it's x plus 2 squared. What do you say, guys? Write, all of you. One thing I should mention, guys, is I already know that some people in probability cheated on my exam. Right? You understand that some people did not heed my advice. They're going to fail without any mercy. If you cheat on my exam and I discover it, I will fail you for that exam. Is that clear? I give you more time to think about it. You can talk to me, but if you share this exam with anybody, if it's posted anywhere, I will fail you. For the exam, for sure. I give you this warning. All right, so a lot of you are saying x plus 2 squared, and you are incorrect. This is not what it means. Of course, there is a confusion in notation. That's why maybe you might imagine that this is the meaning. This is what it's supposed to mean, guys. This is supposed to mean, maybe it's better to write like a circle here, so there is no confusion. This means f, and inside of its belly, f of x. It's a composition of f with itself, which means it's f of x plus 2. Which is what? Now, can you tell me what it is? Yes, so it's f of x. We will mention for a moment why you might have made that mistake. Okay, what is f of x plus 2, please? Exactly, it's x plus 4. Because look at it, what is this function doing? Forget about the x. This function, whatever it digests, it adds 2 to it, you see? Give it an input, and the input is increased by 2. So x plus 2 is the input, so it's increased by 2, so it will be x plus 2 plus 2, which is x plus 4. Yes? Now, what do you think is f of 3 of x, please? Yes, it's a composition of f with itself 3 times, and yes, Francis, it is x plus 6. So this is x plus 4 plus 2. It's really the previous function plus 2, so it's x plus, you might even notice the pattern, 3 times 2. Better to do it this way. Do you see why? I don't need to over-explain. Yes, it means that F has eaten F that has eaten an F. Good. And so, guys, you notice that similar to those numbers, there is this situation. If I have Fn composed with Fm of x. In other words, what this means is that the function that is the result of f eating itself n times, composed with f eating itself m times, will also have this exponent property, which is fn plus m x. Do you agree? Can you see that, guys? Yes? Because what is this? This just means that the function is composed with itself altogether n plus m times. So it works just like multiplication. Agreed? And it's a very difficult thing to study. So fn of x for our case, it's simply x plus n times 2. For this very simple function, it's easy to find notation for it. Okay, so because we have this composition rule, that f to the n composed with f to the m is f n plus m, we can think of f inverse f minus 1 as undo 1 f. F minus 2 means undo 2f in the composition, if it's possible. Do you understand? And then we will say f0 means apply function 0 times. So for instance, just to be sure, guys, what would be for this function is f0 of 7? What would that be? Exactly. The answer is 7 because it means apply the function 0 times to 7. Good. So the answer is simply don't do anything. It's the identity. Understand? So that's why the notation f inverse composed f, it's f to the 1. That should be f to the 0, which means do nothing. Because you canceled one application of f whenever that's possible. Okay. Now there is of course trouble in notation. You see, guys. So sine 2 of x should have been sine with sine x, but instead the notation has a conflicting meaning. Whereas this is just sine of x squared. Okay, that's by accident because people used notation that is contradictory, that is not matched, and it has stuck with trig functions and with some functions and not with others. You understand? So if you have to, of course, not to be ambiguous, you can represent, let's say, function composition as a circle, maybe 3 or something like this. This means compose the function 3 times if you want to use that notation. Good? So here is where I did a bunch of those examples. Now, guys, it's your turn. Here we have, just to be sure, here we have f of x equal to 3x. I would like you to tell me what is f for x, f minus 1x, and f minus 3x, please, for this function. Okay, so be careful. First, it's 4 times. You're saying it is 12x. Be careful, guys. We're gonna do it. Let's see what we get. So let's see. So we have the function is f of x equal to 3x, yes? So what is f2 of x? Let's just see that. This is f applied to 3x. Do you agree? And what is it telling us to do? Multiply by 3. So the answer is 3 squared x. Yes? Because it's multiplying it again by 3. So if I have f3 of x, that would be the same as f applied to f2 of x, which would be 3 times 3 squared x, altogether 3 cubed x. And so f to the power of 4x is equal to 3 to the power 4 times x. Good? Or fraction, there could be, what do you mean by a fraction, Francis? In this particular instance, when I apply integer compositions, positive integer compositions, it will be 3 to the, but what do you mean by a fraction here? In this particular example, just 3 multiplied by itself. Yes, well, that's a very good question. You see, Francis, that's what what would composition that's already a great question. Like if I have f to the 1/3 of x, what would that mean? Can it mean anything? And that's already where you begin doing mathematics. Let's say so. I do not know of right away of a useful meaning of that, but why not? You see, can you come up with a meaning to fractions? You see, right now we have function compositions applied once, twice, 3, but what does it mean to apply the function 1/3 times? Can you find a meaning for that? If yes, then you can create some sort of mathematics that may or may not be useful. So guys, what is this type of thing? Composition of functions about? Maybe I will show you my screen again. And do you see those pictures? So you see, for instance, this picture, which I used as a symbol for my YouTube channel. Yes, you see this picture? And do you see? You can see, for instance, this picture. Yes, and you can see this picture. What are they? What are those things, guys? What are those things? Do you know? So this is dynamic under composition of functions. It's basically the idea is wherever you see this blue region, guys. Any point that starts in this blue region, it shows what happens to this function under what you call a destiny. Okay, let me try to explain what is this. If you're interested, I mean, I'm not sure if I should bother you, but because it's off topic. But this is specifically dynamics of iterations. What happens in the limit if you apply the function at a point many times? Okay, so if you take, for instance, x squared, if you take the function x squared, right, and you begin with the point 0. So 0 is mapped to itself. You agree? If you apply x squared to 0 repeatedly, right? So this is my function. If I apply fn at 0, it will still be 0. You agree? what will happen if I apply at 0, if I apply, let's say, at 1? F of 1, always 1. You agree? So basically 1 by this function is always mapped to itself. Now what happens to minus 1? Minus 1 is mapped under F to 1, and then it always keeps fixed at 1. You agree? You see what happens here? And then if you take a number bigger than 1, if you take t bigger than 1, then what would happen? What you have is you have t becomes, after applying f, becomes t squared, which is bigger. And t squared, after applying the function again, becomes what? What's this number? If I start with t bigger than 1, applying squared will be squared. What would that be now? Write in the comments. T squared, you see this is the function, right? Applying the function, it becomes t squared. Applying a function again, what does it become? No, it's not t cubed, because you are squaring the square, so it becomes t squared squared. So it becomes t to the power 2 squared. And then apply squared there, it becomes square this again. It's like you are adding, what happens there, right? So you square it again. So squared squared, that means what? Yes, so t squared, so it now becomes t squared squared, all of it squared, so it becomes becomes 2 cubed. Do you see that? Do you see that, guys? 2 cubed now. Why? Because simply t to the power of 2 to the power of 2 is what happened in the previous step. Now I square this. So the result is t 2 to the power of 2 times 2. That's how you combine it. Now, how many times do you multiply by 2? So it's t to the power of 2 cubed. That's the formula. Do you see that? Yes? And what would be if I apply f again? And if I apply f again, it becomes to t to the what power? T to the power, to the power of 2 to the 4. Be careful. 2 to the 4. Good. And so what will happen to this number? So that means this number, guys, will go in this pathway. It will converge to infinity. And what you would see is that any number that starts closer to 0 than 1 will converge to 0, and every number that is bigger than 1 or negative will go to infinity. Okay, that's what you call a simple dynamic. So the destiny of anything that's not a distance of 1 unit away from 0 will either go to 0 or to infinity. And this is a simple type of dynamic, and any other pictures that you see are more complicated motions. So everything in the blue in those pictures will eventually go to, well, depends on the particular dynamic, but they will have the same behavior. Okay, so that when you saw those pictures of the Mandelbrot set and fractals, what is it about? It's a sort of movement of particles under a certain force. Now, please calculate f inverse of x. What is this? F minus 1 of x, if this is the function. Okay, so this would be 1/3 times x, yes? X over 3, very good. So the answer here is for B is, here is, by the way, guys, let's just develop a way to solve those questions so we understand what we're asking for. The inverse must cancel the action of f. So here, if I feed f inverse of x into f, they will cancel each other. But f, whatever is the input, it multiplies it by 3. You see? So f of f inverse of x should be x. But it's equal to 3 f inverse of x, which means f inverse of x is equal to x over 3. Do you understand? I'm showing you that so that you understand what's the idea of calculating the inverse in more complicated situations. Good? You see how we reason. F inverse of x is supposed to undo f. So if I plug it inside of the belly of f, it will kind of just pop it off. They annihilate one another and you're left with the initial input. But f applied to anything in its belly is 3 times what's in its belly. Yeah, we will. It's coming down, right? So the result is that f inverse of x is x over 3. And then, guys, what is f to the f of minus 3 of x? This is simply, you can do it this way. It's f minus 2 of f minus 1. Which is f minus 2x over 3. So that's f minus 1. It's basically, it's like applying f inverse to itself 3 times. You see that? F inverse to itself 3 times. That will cancel 3 copies of f. So the result would be x over 3 cubed. Clear? F to the minus 3 will be f, it would be x over 3 cubed. Very good. Now here, guys, we begin with the task of calculating inverses. Could you please calculate the inverse of A? What's the inverse of A? All right, so this hopefully is a simple one. Yes, guys? So what should that be? Look at it. Let's solve it methodically. Let's solve it methodically, guys, here, so that you understand what we do here. We are going to let y, let me even write it in red. We're going to write y equal to f inverse x. And the reason we write y, guys, is that it just saves us the time of writing many symbols, you see? So then what happens, tell me please, what happens if I take f and I feed y to it? What would happen? Tell me what should be the answer. Y is f inverse of x. What is the answer? Look at it, y is f inverse of x. So f of y is f of f inverse x, yes? So the answer should be, well, look, not y, look at it. Y is f inverse of x. The answer, you can see here, f inverse and f, they cancel each other out. The answer is x. Yes. In other words, the answer is y does not stand for the initial input. X is the initial input in my language here, in my sentence, yes? So f inverse of x composed with f should get me back to x. Yeah, so it is f1 minus 1, exactly, Francis. They cancel each other out to 0. So you apply 0 f, so it should be x. Now, what in practice is this giving us? You see, remember that y is f inverse x. So I'll just erase this. Well, let me actually keep it. So then in practice, if I begin with A, what happens there? So I have, in practice, I have f of y. It's supposed to equal to x, but f of y, push anything into f, and you will get 5y plus 8. If you remember in school, they told you to swap, they told you to do something like this in school. They told you, and I write it in blue. In school, they told you to write something like y equal to 5x plus 8, and then just write x, swap the variables, equal to 5y plus 8. That's how they taught, I think, in your school, how to solve this. Am I right? Now, what have they really tried to explain? I mean, if they try to explain it, what you really are saying is there's no swapping or anything like that. It's much simpler than that. What is happening, guys, is this is why it looks like you're swapping variables, because y represents the inverse function, and if you push the inverse function into f, then you get back the initial input. But the function processes anything you push in its belly as 5y plus 8. You see, it's just a way to save on notation, right? To save on, instead of writing x equal to 5 f inverse x plus 8, it's much simpler to write y. But this is really what's happening. Understand? It's 5 f inverse of x plus 8. Everything clear? So what would happen is that you have now x minus 8 over 5 is y. So my expression for the inverse is f inverse equal to x minus 8 over 5. Good? All right, wonderful. Now, very quickly, if it's good, tell me the answer for B. Very good. The answer is 1 over x. It's itself. The inverse function in this case is itself. I don't need to explain. Yes, guys? The inverse function in this case, it's called involution, is the function itself. It cancels itself. Now, please tell me the inverse for C. All right. So Humira says it's 5 plus x over x, and a bunch of you, I guess, be careful to write parentheses. I mean, maybe you all mean the same thing, but if you don't write parentheses, then it means just x plus 5 divided by x. So x only divides 5 if you don't write parentheses. Okay, so let's see what's the answer for C. We can scroll down and we can just, again, the result is we set y equal to f inverse of x. You agree? So that means we get x is going to be equal to f of y, but f processes any input by saying it's 5 divided by y minus 1, by the input minus 1. Good? So then I divide by 5 and take reciprocals. So 1 over y minus 1 is x over 5. Taking reciprocals is 5 over x equals to y minus 1. And so what do we have? We now have that y is equal to 5 over x plus 1, or when I bring it all together, it's x plus 5 over x, like many of you have written. Good? All right, then please do number D very quickly. Okay, good. Okay, very good. So D is the cube root. You all see that, yes? D is the cube root. Now, guys, the only ones that are somewhat challenging, if anything, then try to see if you can solve E, and then we'll try to solve F. Solve E. All right. So again, guys, of course, with this question, so how do we solve it? How do we solve it directly, right? So we can see directly. Let's look at this question, yes? So we have that x is equal to y minus 1 over y plus 1. Agreed? Now, what can you do? You can do many things here. You can, if you want, to multiply by y plus 1 on both sides. So it's x, y plus x. I just multiplied it across is equal to y minus 1. And I would like to solve for y. So I will just move the y across. And I have x minus 1 times y is equal to minus x minus 1. Agreed? So then when I divide, we have what? We have y is equal to minus x minus 1 divided by x minus 1. Yes? Divided by x minus 1. Which is, well, you can write it in so many ways. You can write this as, if you prefer, as x plus 1 divided by 1 minus x, or better, 1 plus x divided by 1 minus x. Yes? All right, good. Now solve question F, please. There is also a quick way to do that, but we'll see if I'll show you or not. On E, Giovanni, you see the idea for E is what? This step. Is this step clear? So x equal to y minus 1 over y plus 1. This step clear? All right, so then all you do, you need to solve for y, because y, if you remember, is f inverse x, yes? Y is f inverse x. So how do you solve for y? Just multiply both sides of the equation by y plus 1. So you get xy plus x equal to y minus 1. And then you are solving for y. So you move the y across and everything that doesn't have a y across. So you can write it as, for instance, so you can write it as x minus 1y. Do you see what I did? I took this 1y and this, and I moved it here and factored out y is equal to minus 1 minus x. And then I solve for it. Make sense? Yes. And, okay, so one person already solved for the next question. So yeah, so let's see. This is what happens with the last question. So here we switch x and y. So we have y to the 5th minus 2 over y to the 5th minus 7 is x. And I first broke it down. I decided to make it simpler. So I see here y to the 5 minus 7 on the denominator. And I would like the numerator to be the same, because then it cancels to 1. So what do I write? I write y to the 5th minus 2 as y to the 5th minus 7 plus 5. Do you see why I did it? Because I can take this number in the denominator and divide in here and in here. Are you with me? Basic algebra idea. What does this achieve? This achieves the eradication of, you had 2 instances of y in this equation, now you only have 1. Do you see? This divided by that is 1 plus 5 divided by the denominator. So I used to have a y in the numerator and a y in the denominator. Now after doing this, I only have one y. So then what do I do next? I then move the 1 across and take reciprocals. So this is x minus 1, and I took reciprocals to get y to the 5th minus 7 on the top. So y to the 5th minus 7 is now 5 over x minus 1, which means y to the 5th is 5 over x minus 1 plus 7, which after combining gives me 7x minus 2 over x minus 1. And all I have to do next is take the 5th root of y. So it's just using those algebraic steps, guys. I'm not sure if we're not usually going to solve inverses, but with the questions that I've given, it's much simpler to find the inverse. So for instance, if you had have this function, guys, so you had the function f of x equal to, I don't know, 10x plus 2 over 3x minus 7, yes? What is the inverse of this function? I can solve this inverse function, I can solve it instantly, yes? So for instance, what's the answer? It's minus 7x minus 2 divided by divided by God damn it. Divided by 2, not my day. You know what, guys, not my day. I don't want to bother you with this today. Later. So here is basically what this all has to do with calculus. So graphs of inverse functions, guys, are in fact not very different from the original functions that gave birth to them. Now, why is that the situation? Let's look at this function. This is the graph x f of x. Okay, you can see that for each x there is a unique y, so this is an invertible function. Good. So if you draw this graph, it means here are the inputs and the y are the outputs. How can you see the inverse function? The inverse function is here you have y are the inputs and x are the outputs. Do you agree? So for instance, if I have the points x, f of x, you see? So this is the process. Now if I were to apply f inverse to both coordinates, right? So this would be if this is, so you see what, so this is x f of x, and this point can also, if you write this as y, then this is f inverse of y. That's the same notation. So let me try to show you with this drawing. So guys, this graph is when you say this graph is part of y equals to x squared for the positive part of the x-axis. Yes. What does it mean that y equals x squared? That simply means that the second coordinate is the square of the first. Do you agree? Second coordinate is the square of the first. But it's the same way you can say it in passive. But you can say this as the first coordinate is the square root of the second coordinate. Do you agree? You understand? It's said in reverse. From the perspective of the second coordinate, the first coordinate is its root. So they are producing the same exact picture. Are you with me? It's very important and involves your spatial imagination. Are you understanding what I'm saying so far? Are you sure, guys? So notice then, if you have to describe what's happening here. So if you're just today I watched this documentary about Russian astronauts. Yes. So imagine that you are a cosmonaut and you're walking on this x-axis, right? And then you look at this curve. What do you report? If you're standing at position x, you report that my position is that my altitude is the square of my position on my horizontal line, right? The altitude is the square of my latitude, let's say. I don't know what you call it. Good. Now, looking at that same point, what would an astronaut or a cosmonaut walking at this position y? For this astronaut, this is the horizontal axis. Do you agree? If there is no gravity, I mean, you see, this is horizontal. It's relative, right? This guy thinks that the x-axis is horizontal. This guy thinks that this axis, the axis y, is horizontal. So what does he report? He reports that the altitude is what? The altitude is the square root of the longitude, right? So, and to keep the information all together, he reports root y, just so that they have the same coordinates. It's just for this guy, for the guy walking on the y-axis, this is vertical. Do you agree? I hope you're not confused, guys. It's just don't get disoriented. That's why traveling to space is so very dangerous. In fact, I had many terrible dreams, like in those fractals, that I'm spinning, and as I'm spinning, I try to keep my orientation, try to keep calculating where am I located, and I know it's useless because I'm going to sink into that terrible abyss that I showed you. My dreams that I'm sinking into that. Into the mouth of this creature. Yes, if you zoom in, you would see those same complicated, every point is that complicated shape. So this guy tells us what? Here is the general situation. Here is the general curve, right? And the inverse is viewed exactly by the guy walking on the y-axis here. This guy, if this is the function, viewed this way, the inverse is understandable if you walk on the y-axis. Do you see why? Because you see, just if y is equal to f of x, then f inverse of y is equal to x. Right? This identify the same curve. That's just a difference between passive and active tense. So here is what it means, guys. Look at it. You see, here is this picture. I wrote a blue dot and I placed a red dot so that you can see what happens. It's just presentable or polite to present the graph of the inverse in the same way as you present the function itself. So what you're supposed to do is you're supposed to make this vertical line, you're supposed to make it horizontal. So first, how do I do that? I can rotate by 90 degrees. So this arrow where you see the red is pointing this way. But this arrow, if I rotate by 90 degrees, is pointing down. All I have to do now is flip it around, and this is what I get. And this is the graph of the inverse. It's really the same picture, but just change your point of view. You understand what I'm saying? It's very important, guys. What I'm saying is that the graph of the inverse map geometrically is the same as the original, which means that you are in some sense not creating a new function. In some sense, you know everything about this function. In some sense, it's just looking at the same function, but with a reversed perspective, with a different perspective. You understand? If you follow what I'm telling you, then you understand that inverse sine and sine are essentially, there is much to them that is the same. They're like the same function. Logarithm and exponential are the same because they are just change of perspective of the same shape. No, it would not be. It would not be because you're trying to take the vertical and make it horizontal. So look at it. There is a 90 degree between vertical and horizontal. So you rotate by 90 degrees. Yes. You see what happens. Just if you rotate by 90 degrees this axis, here's what I'm trying to say. You see, this is vertical. This is horizontal. If you rotate by 90 degrees clockwise, this is minus 90 degrees if you prefer, what do you get? You get, let's say this is, so that we can distinguish, this is here red, okay? And this here is blue. What happens if I rotate? The red is here, but the blue also rotated by 90 degrees and it is here. So the blue is here and the red is here. Yes? So then what you want to do is just flip the picture. Just if it's a piece of paper, just flip it around. Flip. Yes? And what happens if you flip? then you have everything as you wanted. You have the blue is now on the top, and the red is to the right. So it just that's what you do to see the picture of the inverse graph. It's very important, guys, if you understand what I mean, because if you do, then what every other function we're going to learn right now is the same exact function. You understand? So for instance, if I were to draw the quadratic here, let's just make a graph of the quadratic. Let's make it in green. Okay, this is the quadratic. Okay, now the square root is what you would see if you view it this way. Okay, so then I rotate by 90 degrees. What happens? What happens is that now I have this picture. Yes, I have this picture. And the only problem with this picture is that blue should be up. So then I flip it around and I get the shape of my square root. This is the square root function now. This used to be the square function, but now it now looks like the square root function. They are geometrically the same object, but viewed from a different perspective. Do you understand? And do you understand how I reasoned about it? Guys, it's even in my talk, my brother mocks me because I like to speak in passive tense. I would not usually say you should do the test. I would say the test should be done by you. I like to speak in passive tense. So this is, again, in my mind, very similar to switching between a passive tense and an active tense, or better, switching between perspectives. You see, how can you describe the relationship when you say y equals x squared? You can describe this relationship in two ways. One way you can say second coordinate is the square of the first. And another way you can say the same exact thing, you can say first coordinate is the square root of the second. Both sentences are saying exactly the same thing. They're just saying the same thing in different perspectives. You understand? For the second part, I view the first coordinate from the perspective of the second coordinate. And for the first part, I see the second coordinate from the perspective of the first. Do you understand? So being able to understand inverse functions is very similar to being able to place yourself in the shoes of a different person, which I think very few people are trying to do. Speaking of which, I am trying to read from the beginning to the end, the Old Testament again, just to brush on my Hebrew, and also and I compare it with the English translation. In case anybody is interested in discussing interpretations, maybe we can find time. I enjoy such things as well, right? I usually spend 30 minutes a day doing that. I'm now in Shmot, or what do you call it, Exodus. So if yes, let me know. Why am I interested in it? Because I think also in the Bible, it's a very, very different perspective. For instance, what was promised to Abraham was not immortality of himself. I mean, there's no mention of that, but it says that he will be a great nation. So it seems immortality to ancient people is very different to my notion of immortality, for instance, of what I would imagine immortality to be. Right? For him and for them, it was the existence of the group, for the continuation of the group. Anyhow, sorry for running my tongue. I'm just trying to tell you what I find interesting in general, is that I try to understand as many things that are strange to me as possible. And this is a way for you, a very simple way for you to understand whether or not you can see another perspective. Yes? This is just changing perspective of first coordinate to look at the perspective from the point of view of second coordinate. And if you understand that, then you see the two, the thing that they describe is the same. Are you with me, guys, or at least partially with me? Yes? Wonderful. So this is this can be accomplished in one swift motion, guys. Look at it. If you reflect through the line y equals x, what happens if you reflect through this line? That means this segment, look at it, the y would right away become the x. You see, if you reflect y equals x, then you see this horizontal red line will become the vertical line, which means that it will swap x and y. It will basically change their respective positions. You see, this will slide down, and the red line will connect to x. So there would be perpendicular and in the right orientation. So one reflection through y equals x accomplishes the same thing as carrying those motions separately. All right, so here is, guys, now trying to understand how the derivatives are related. So we have astronauts in position A and position B are communicating with one another. So astronaut A sees the curve x squared, y equals to x squared. Second coordinate is the square of the first. Astronaut B sees what curve? The curve that astronaut B reports is x equal to square root of y. Yes, guys? Now I want to find the derivative of the square root of y. You see, so what can I do? What is the derivative? The derivative means I zoom at this point. Let's say he wants to find the derivative at the point 9. Yes, so he is asking for help of astronaut A. Okay, so he describes this tangent line. You understand, guys? When you describe derivative, you're describing slope of tangent line. Yes, in other words, zoom in at this curve, it looks like a line segment and it has a slope. Although from any perspective, they all see a line, they differ on what they think is the slope. Do you understand? Because this looks like it's flat and horizontal, but if you're walking on the wall, it looks to you like it's perpendicular. You see, so from geometric point of view, there is only one line. Give me a moment, guys, and we will be done. So you see, so this is b equal to 9. Now, what slope is this guy reporting? So this guy sees it's at a point 3. So he is reporting the slope 2 times 3. So he's reporting the slope 2 times 3. Tell me, please, if you understand change in perspective, what slope is this guy then reporting? Look at it, because he sees dy over dx. You see dy, the red vertical over dx, is the slope according to this guy. That's the slope of this line according to this guy. What is the slope according to the guy standing on the y? What is the slope of this line according to him, please? You see, this is just because it's a point 3, we know the slope is 2 times 3. Please let me know what's the slope according to the guy on the vertical line. And then we can go. All right. All right, 2 people see that right away. It's 1 over 6. 3 people see that right away. The answer is 1 over 6. Now, why is it 1 over 6? What's the slope that he reports? It is dx over dy. Do you agree? Because for him, dx is the vertical line and dy is the horizontal. And what's dx over dy, guys? You see, that's Leibniz notation, why it's so useful. It's the same as 1 over dy dx. Right? Let me just show you with better writing downstairs. You see that? The other guy sees the slope as dx over dy, which is 1 over dy dx, which is 1 over 6. So using this communication, he right away knows, even if he does not calculate the slope directly, he just talks, the guy standing on the y-axis at 9 talks to the guy standing at 3. It says, hey buddy, what slope do you see? And he says, I see slope 6. And he says, oh, thank you. Then he knows his slope is 1/6 because he understands how to transform the perspective of another person into his own perspective, which is very difficult, guys. The entire theory of relativity is a transformation of perspective. Do you understand? So it's very, very difficult to communicate one perspective and translate it to another point of view. Wonderful, guys. So then I suppose if you have no questions, say goodbye. If you want to play what, when, where, or have questions, stay with me. And I think Christina had a question about the exam.